Welcome to the next video. Now, in this video, we're going to be covering a very interesting question. Now, why do I say it's interesting? Now, I believe that it is interesting because it is a combination of different concepts, principles, and ideas that we've learned throughout grade 12. So, it is an incredible test to our overall understanding of Euclidean geometry. It challenges our logic, it challenges our overall skills in Euclidean geometry, and it confronts the issues that we may still have in Euclidean geometry. It may confront the learning gaps that you have in Euclidean geometry. It may confront the academic incompetencies that you still have. And so, if you would like to truly test the progress that you've made thus far in Euclidean geometry, this is an incredible and very appropriate question to do so. But without further ado, let's get started. And also, just a reminder before we get started, if you haven't watched part 1 to this video, I have linked part 1 in the description below, because you're going to be incredibly confused and tremendously confused as to what's going on. If you haven't watched part 1, back in part 1, I've illustrated how to analyze the question, how to evaluate the question, and how to annotate the question. Okay, and so I've done all the annotations in the previous question, and so what you want to do is you just want to click off the video, watch watch part 1 to this video, and just understand, internalize the interpretation and analysis process. And then what you want to do is you want to click off the video and come back to part 2. Other than that, let's get started with the video. So now 10.2.1, and I'll just remind you everyone, if you have not watched part 1 to this video, what you want to do is you want to click off the video, click in the link. There's a link that I've attached in the description down below so that you can continue on and watch part 1. Now 10.2.1, we have to prove that DGFO is a cyclic quad. Now let's first highlight DGFO. I'm just going to, so what we first want to do is you just want to highlight DGFO. Now, how do we prove that a shape is a cyclic quad? Well, now what a lot of students do is they make this mistake, and it happens several times. It actually happens very often, actually. So what students think is that, so let's say for instance we have a shape that looks like a cyclic quad. However, we would like to prove that it's a cyclic quad. And so what a lot of students will do is, I'm just going to label this as A, B, C, and D. Okay, so what a lot of students will do is they will say, or they will state that A equals to B, for instance, because of angles in the same segment. However, that is very impractical and unreasonable. It makes absolutely no sense. They will use a cyclic quad. They will use the cyclic quad theorem to prove that it's a cyclic quad. So, and that makes absolutely no sense, because you cannot use a cyclic quad theorem to prove that a shape is a cyclic quad if you don't know it's a cyclic quad. And so what you first want to do is you first want to write down all of the cyclic quad theorems, right? So we have angles in the same segment, we have exterior angle of a cyclic quad, and we also think of opposite angles of a cyclic quad equal to 180 degrees. Now, let's first start off with angles in the same segment. How would we use the theorem of angles in the same segment to prove that the shape is a cyclic quad? Well, the very first thing is that you would have to identify angles that are in the same segment. Now, let's look at A and B. You're not just going to assume that A and B are equal to each other. No, we don't. We're trying to prove that A, B, C, D is a cyclic quad. And so what you would maybe do is you'd prove that A and B have an angle that they're both equal. So you need to prove that A and B are both equal to the exact same angle. They have an angle in common. So for instance, you could prove that A equals to Z using another Euclidean geometrical theorem, or you could use other principles as well. And you could also do the exact same thing with B. For instance, you could prove that B equals to Z using another using a set of other different principles, ideas, concepts, Euclidean theorems. Okay, and so now that they're both equal to the exact same angle, that means that they will equal to each other because they're equal to the exact same angle. They're both equal to Z. And so in doing this, we would simultaneously prove that A equals to B, and as a result, we would then prove that A, B, C, D is a cyclic quad, because we proved that the angles that were in the same segment, A and B, were equal to each other because they were equal to the exact same angle. Okay, and that's exactly what you can do to prove that a shape is a cyclic quad. What you can also do is you could prove that the angle A, for instance, is equal to a certain numerical value. So you could prove, for instance, that it's equal to 40 degrees. Okay, you could also prove that B is equal to 40 degrees. And so, since they're both equal to 40 degrees, that means they're equal to each other because they have the exact same numerical value. And so, in doing this, we would also prove that ABCD is a cyclic quad. Now, let's look at exterior angle of a cyclic quad. I'm going to label this cyclic quad ABCD as well. Okay, so now let me actually label this part as F. So so this is no, this is F1. I'm actually this is F1, F2, and just forget about that part of there. Okay, so we have A, C, F, B. Now, we want to prove that AFCB is a cyclic quad, and we want to do this using the exterior angle of a cyclic quad theorem. And so we first have to identify the angle that is at the exterior of the or of the shape that we would like to prove is a cyclic quad. So we can clearly see that F2 is at the exterior of angle ABFC. Now, what is the opposite interior angle to F2? It is angle A. And so we have to prove that angle A equals to F2. How exactly will we do that? Well, you're going to use that exact same idea that I illustrated previously. What you need to do is you need to find an angle that they might have in common. So maybe they're both equal to, it might be a part of a larger diagram. Maybe they're both equal to Z, for instance. A equals to Z using a set of other different principles and ideas. F2 might also equal to Z using a set of different principles and ideas. And so since they're both equal to the exact same angle, they're both equal to Z, that means that they would equal to each other. And as a result, you'd also be proving that A, B, F, C is a cyclic quad. Or what you can do is you can prove that A equals to a certain numerical value. It might be 20 degrees. And then you might also do the exact same thing with F2. You might also prove that F2 also equals to 20 degrees using a set of different principles and ideas. And in doing so, you'd prove that F2 equals to A because they're both equal to 20. I do not want to see any students making the mistake of thinking A equals to F2 because it's a cyclic quad. No, we're trying to prove it's a cyclic quad, okay? So please do not make that mistake. Okay, so now, what if you want to use opposite angles of a cyclic quad are equal to 180 degrees? How will we continue on with that process? Okay, so I'm going to label this as A, B, C, D. And so what we want to do is we could prove that A equals to 100 degrees using a different set of principles, ideas, and concepts. And we could prove that, just these are just examples, by the way. We could prove that D equal to 80 degrees using a set of different principles, ideas, and concepts. And so while proving that A equals to 100 and D equals to 80, when we add those two values, it will amount to a value of 180 degrees. And that in itself proves that A, B, C, D is a cyclic quad. Now, why is it a cyclic quad? Because the opposite interior angles, we have to understand, a lot of students don't even understand what the terms are. Think about it. Take it as face value. Opposite, A and B are opposite from each other. Interior angles, meaning that, or implying that A and D are within, they are at the interior of the shape. And so if we're able to do that, 100 A equals to 100, D equals to 80, you add the two values together, and that amounts to 180, and that in itself proves that it's a cyclic quad. Okay, so now we can pick, you can use any of these options. Just list these options. Make sure that you conceptualize it efficiently. Make sure that you understand how to apply these methods and ideas. Okay, now we have to prove that DGFO is a cyclic quad. Now, what I always suggest is you just want to pay very close attention to the annotations that we've made. You want to pay close attention if we have any angles within that shape. You want to pay attention to if we have any 90-degree angles perhaps in the shape, which we do. We've labeled G4 plus G3 as being equal to 90 degrees because of angles in the same segment. Not angles in the same segment, sorry. Angles in a semicircle. So now, remember that we've identified D. Let's just go back. I just want to give you guys a quick reminder. We've identified DE as being a diameter. And if it's a diameter, diameters will always subtend a 90-degree angle. And so what you want to do is you want to start tracing the lines from the diameter all the way to the other end of the circumference of the circle, landing over here. Do the exact same thing on the other side. Trace it, trace it, trace it, trace it. It ends over there, meaning that it ends right over here by G4 and G3, meaning that G4 plus G3 will equal to 90 degrees. And so O equals to 90 degrees because that is just the general information that was provided to us in the segment. And so we know that G4 plus G3, or G4, you can also label it as DGF plus the O is equal to 90 degrees. and that in itself will prove that it's a cyclic quad because the opposite angles, the opposite interior angles of that shape amount to 180 degrees. And so there is a certain way that you have to structure your questions, or everything will just, you will not receive any marks whatsoever. And so you have to see the fact that DOB would be the O, the center, the O part. Remember, it's 90 degrees. That's something they've already provided to us. DOB equals to 90 degrees. DGF, which is G3 plus G4 equals to 90 degrees because of angles in a semicircle. And then you have to formulate and construct a little equation for yourself illustrating that DOB plus the G3 plus G4 equals to 180 degrees. And then you have to substantiate your final statement by stating that DGFO is indeed a cyclic quad converse. Now, pay very close attention. Now, the reason why we have to add the term converse is because we attempted to prove that a shape is a cyclic quad. We didn't know just yet that it was a cyclic quad. And so if you would like to prove that a shape is a cyclic quad, a tangent, and we are trying to prove that that shape is a cyclic quad while using cyclic quad geometrical theorems, like we used opposite angles. We tried to prove that opposite interior angles were amounted to 180 degrees. You have to include the converse opposite angles of a cyclic quad because we tried proving that it's a cyclic quad and we were very successful in doing so. And so, now the next thing that I want you to do is be very careful. The minute you prove that it is a cyclic quad, I would like for you to treat it and acknowledge the fact that it is indeed a cyclic quad. Now, what you want to do is you want to go back ahead and label the different parts of the cyclic quad using your cyclic quad theorems. Let's first start off with angles in the same segment. Do we see any angles that are in the same segment in angle D, in shape DGFO? No, we do not see that bow tie shape, so that's not going to work. What about exterior angle of a cyclic quad? Let's identify some of the exterior angles of cyclic quad DGFO now that we indeed know that it is a cyclic quad officially. We can clearly see that F1 is the exterior angle to the cyclic quad, so F1 will equal to the opposite interior angle, which is D. Now, are there any other angles that we see as being equal to the opposite interior angle because of angles in exterior angle of a cyclic quad? Yes. O, this part of O equals to G4 plus G3, which is also 90 degrees. And that makes complete sense. Why is that? Well, because we could easily calculate this part of O being equal to 90 degrees using angles on a straight line, since we already know that the other part of O is also 90 degrees. So that's pretty easy. Out of the last part, opposite angles of a cyclic quad are 180 degrees. So we're just going to keep that at the back of our minds. We're just going to hold that thought and we will be applying that principle if it is necessary. Now, next question. B, we have to prove that GC equals to CF. Okay, so now let's first identify. Okay, so we just want to identify GC. What we want to do is we always want to go back and highlight it, GC and CF. And so, how do we prove that two lines are equal to each other and that so happen to be a part of a triangle? What you need to do is you need to prove that the opposite interior angles within that triangle, opposite interior angles are equal to each other. And so, G2, we have to prove that G1 plus G2 equals to F. That's the goal. And so, that is what I always recommend and encourage students to do. Now, before you approach a question, before you start, before you try to process it, before you try and break it down to its very simplest form, you need to write a goal. You need to highlight and outline what your goal is. The goal is to prove, I'm just going to write it down. Our goal is to prove that F equals to G2 plus G1. And so here's a simple process and method that you can apply. If you want to prove that the two different sets of angles are equal to each other or one angle is equal to another, what you need to do is you need to use your column method. And so I'm just going to put this as I'm just going to draw in columns. Each column or each line segment separating each and every single angle. Now, this will be to your great advantage if you use this column method, okay? The next thing that I want you to do is I want you to list all the angles that each and every single angle that are a part of the column or that is a part of the column is equal to. Now, let's first start off with F. What angles are F equal to? We want to use the color annotations or the color coordinated annotations as guidance. Now, you can clearly see that F, by the way, this is F1. F1 equals to D. We've marked them off as both being equal to red. Let's pay attention to G2. What angle is G2 equal to? What have we marked it off as being equal to? Now, in the previous question, maybe it's something I did not explain. This is very important. Now, I'm pretty sure we marked off G1 as being equal to A, which is correct. If you don't understand why, please click off the video, watch part 1 where I explain it. However, when you think of tan chord theorem, this is very important to remember. A lot of students forget this. You need to ask yourself if that angle is a part of a larger angle. So we know G1 is a part of G1, G2, G3, G4. And so what you want to do is you want to draw a line starting from the tangent, which is DC. You want to draw it, and you want to enclose both G1 and G2 around this line that you will be drawing. Okay, and it ends over there. Then you need to identify the line that the circular annotation ends on. It ends right over here at GE. So GE is obviously our chord. We have to understand what a chord is, everyone. It's so important. A chord is a line that carves out different segments of our circle, um, resulting in just like I said, resulting in a segment being formed. And so what we want to do is we want to identify the angle that that chord subtends. How do we do that? We're going to take our lines on both ends of the circumference of the circle and trace it to the other end of the circumference of the circle. So we're going to trace it. It ends over there. We're going to take the other end of the chord, trace it, trace it, trace it, trace it. It ends over there. And so now we know that GE subtends D. Okay, it holds D to the circumference of the circle, meaning that G1 plus G2 will equal to D because of the tan chord theorem. We know that both G2 plus G1 is equal to D. Okay, so the combination G1, yes, is directly equal to D. However, we know that G2 plus G1 equals to D, and we can clearly see that they have an angle that they're both equal to. Now, before we continue on, I just want to make sure everyone understands exactly what I said previously. So important. Now, like I said previously, if you see that an angle is a part of a larger angle, in this case, we have G1, G2, G3, G4, we first want to start off by identifying the tangent, which is GC. So you just want to go back and highlight that, and then identify the chord. The chord in this case would be GB. GB is the closest chord to GC. And so we know that G1 will equal to the angle that GB subtends, right? So you want to take your pencil, trace it all the way to the other end of the circumference of the circle, do the exact same thing on the other side. It ends at A. So we know that A equals to G1. Now, after identifying the fact that G1 equals to A, there's another step to the process. You want to highlight and annotate the other parts of the G angle. So take it step by step. Now we want to draw a line around G1 and G2 and see which line that it ends on. We highlight G1 and G2, it ends on GE. Highlight GE. GE is our chord. Remember, G is our chord, and then GC is our tangent. Now, what we want to do is we want to identify the angle that GE subtends. How do we do that? Take our pencil, trace it all the way to the other end of the circumference of the circle. Do the exact same thing on the other side. So we know that GE subtends D. What does that mean? That means G2 plus G1 equals to D. Do the exact same thing with G1, G2, and G3. Start off with G1, highlight G1, G2, and G3. It ends right over here at AG. Now, the reason why this is not going to work is because GA does not subtend any angle. And so we will stop right over there. So we can see that F1, G2, and G1 have an angle that they all have in common. And so what we want to do is we want to verify that yes, indeed, we've proved that F1 equals to G2 plus G1. The reason is because they have an angle that they all have in common, which is D. But there is a certain way to structure your answers, or everything will it will not work at all. And so you first have to state the fact that F1 equals to D because of exterior angle of a cyclic quad. Then you have to state the fact that G1 plus G2 equals to D because of the tan chord theorem, and therefore F1 equals to G1 plus G2 using the method. By the way, if you're going to use, and please, everyone, if you actually do struggle with Euclidean geometry, it will be to your best interest to implement and use the column method that I've showed you. And so you're not going to use your column method as a part of your steps because the marker will not understand what's going on. And so you just want to make sure that you substantiate your answers, you validate your answers by stating the appropriate theorems. Okay, and that leaves us with F1 equals to G2, G1 plus G2. And so now that we've proved that F1 equals to G1 plus G2, As a result, we've also proved that GC equals to CF because of sides opposite equal angles. Now, usually we would have two lines that are equal to each other that are part of a triangle. So usually we would have those two lines that are equal to each other. And so we would state that, for instance, angle A equals to angle B because of opposite angles equal sides. But now that we've proved that the angles within that within the triangle are equal to each other, so that we could prove that the lines are equal to each other, you're going to use the other, it's going to kind of be the opposite. You will say that sides opposite equal angles. Okay, everyone. Hopefully you found this video very helpful. Make sure you click off this video, and if you are writing soon, make sure that you go and you binge watch every single video that's been posted on this channel thus far. If you have, you will start to see that Euclidean geometry is actually incredibly easy. As with, the more you practice, the easier that it becomes. It will literally become very natural to you. Okay, but just like I said previously, if you'd like to receive the PDF version, make sure to send an email. Be sure to send an email. Consider leaving a comment down below. But without further ado, we will see you in the next video.